Hello viewers, welcome to today's lecture on data and signal. This is the third lecture on this series of data communication. In this lecture, we shall cover various aspects of data and signal. On completion of this lecture, the students will be able to explain what is data, distinguish between data and signal, distinguish between analog and digital signal, explain the difference between time and frequency domain representation of signal, specify the bandwidth of a signal, explain the bit interval and bit rate of a digital signal. And here is the outline of this of today's lecture. First, we shall consider data and data types, analog and digital data, signal and signal types, examples of analog and digital signals, periodic signal characteristics, time and frequency domain representation of signal, spectrum and bandwidth of a signal. Finally, the propagation time and wavelength. First, let us consider what is data. As we have seen that we have to send data through some communication media, and we have to understand what do we really mean by data. Data is an entity that conveys some meaning based on some mutually agreed upon rules, conventions between a sender and a receiver. That means, a data, for sending the data, the sender has to follow some mutually agreed upon rules and convention. At the receiving end, the receiver also has to follow mutually agreed upon rules and convention to interpret that data. Let us take up an example. Say we have sent, the sender has sent some data, say 1 0 0 0 0 0 1, that has been sent by a sender. Now, as such, this bit sequence has no meaning, and the receiver cannot really understand what it is and what for it has been sent. But once it is told that an ASCII character has been sent, as you know, ASCII stands for American Standard Code for Information Interchange, and whenever the sender sends that informs that this is a ASCII character, receiver will know that an ASCII character has been sent, which is nothing but the character code for the character A. That means, A has a 7-bit code 1000001. So, now it has become data. Until it was able to be interpreted, this receiver is able to interpret, it is no longer data. For example, we hear many noise disturbances in the from the environment, but we do not interpret everything as data. But whenever we hear a music or song, then we know, then we can interpret it and we can understand the meaning of that song, and that can be considered as data. That means, uncorrelated, incoherent signal or information whatever we receive is not data. What we can interpret, obviously that interpretation is based on some knowledge of the data. That means, some standard, some norm, some mutually agreed upon convention. So, this is your significance of data or meaning of data. Now, question is, what are the different types of data possible? Data can be either analog or digital in nature. So, data can be either analog or digital. Analog data have continuous values over time. That means, suppose this is the time domain representation of some data, and say, so it has continuous values over time. So, this side is the time and this side is the, say, amplitude in this case. So, whenever this is being sent, then this has continuous values, that means it has got infinite number of values within this range, then it has got this, then we call it analog data. You can see the within this duration, say time 0 to time, say, t, a large number of values or infinite number of values have been sent. So, that means the signal levels can vary from 0 to some range, within some range, say a max, any value within that range, then we call it analog data. So, this is the example of analog data. For example, voice and video are analog data that is being commonly sent over medium. First, let us consider the audio or audio as an example of the analog data. As you know, a person who is sending, maybe say a person is sending by mouth, say suppose somebody is speaking, this is the mouth and here is an ear, somebody is listening. Now, through ear the voice goes to the ear. That means, from the mouth the vibration is made, that vibration leads to some compression and decompression, as you know, waves, and that wave conveys the data to the ear and it creates some sensation in the eardrum which we hear. So, this is your audio or acoustic data. Now, if we represent it on some say on time domain, if we want to represent it, suppose we want to represent it in time domain, or let it be instead of time domain, let me represent it frequency domain, that will be more clear. So, here we write in frequency domain. F, and the signal strength usually lies in the range of maybe 0 to, it can be 3500. Significant portion of the signal lies in this frequency range. However, as we know, a voice or a music can have any signal in between 20 hertz or 20 kilohertz. However, our ear is more sensitive to this range of the signal, that means 0 to 3500, and most of the voice communication take place within this range. So, this is the analog data or audio data that can be communicated usually through air. However, we cannot send it electronically. To send electronically, we have to do something that we shall see later. So far as the video data is concerned, we are familiar to viewing image on the TV. In the TV, as we have seen, how do you the video data can be best explained with the help of what we see on the TV. As we know, on the TV, a raster scan moves, an electron beam moves from this end to the other end, large number of times, and that is how a frame is created. And this is the number of lines is about 525 lines. Of course, all of them are not visible, of which 483 lines are visible, the other lines are blanked, and it is done in an interleaved manner. That means 241 and half times it is repeated, twice it is repeated, and it is repeated 30 times in second to make it visible on the screen. That means for the sake of retentivity of the eye, the repetition rate should not be less than 30 times, otherwise the image will not appear to be stationary. So, whenever we do this, the bandwidth requirement of this video data is about 4 megahertz. 4 megahertz, of course, this is excluding voice and color. If we include that, it will be more than this. So, this is the example of video data that we receive through television network, and we see it has got much higher signal components having bandwidth of about 4 megahertz. This is an example of another analog data. Now, let us consider third type of analog data, that is physical parameters. Physical parameters are essentially various parameters that we encounter in environment. The world that we belong to is in analog domain. That means, all the physical parameters are analog in nature. For example, temperature, say temperature, pressure, these are all analog in nature, and these analog parameters usually is converted to electrical form with the help of transducers. Transducers are essentially some kind of energy conversion device. So, on this side we apply physical parameter, it can be temperature, pressure, say light intensity, and on this side we apply that, on this side we get some electrical signal, voltage or current. So, this is your transducer, and transducer produces here a signal, an analog signal, which is electrical signal, which is also analog in nature usually. That means, we get continuous values of the electrical signal corresponding to the physical parameter on this side. It can be for any one of the parameters that I have mentioned. So, these are the examples of analog data. Now, let us consider digital data. Digital data take on discrete values. Discrete values means, suppose we have so digital data take on discrete values. Suppose here is your, again in terms of time we are representing, it can have say 1, 0, 1, 1. So, these are the discrete values. That means, two distinct voltage levels. Here it is 0 volt and it can be say 5 volt. it is represented by two different voltage levels. So, 0, 1, 1, 1, then it can be again 0 and 1. So, it has got, as you can see, it has got two different voltage levels. So, here it takes on some discrete values. It is not absolutely necessary that it should have only two voltage levels, it can have more than two voltage levels, but in general we are more concerned with digital communication. So, it will be essentially of two levels, as we shall see in most of the cases. An example of digital data are text or character strings. As we have mentioned that ASCII characters are of 8 bit. Here we see as an example some ASCII characters. So, American Standard Code for Information Interchange, ASCII codes, these are 7-bit codes. Some of the codes are given here. For example, 0 is 001, 0000, then 1 is your 011, 0001, that is the ASCII code for 1. That means, in the computer, whenever we press a keyboard and press the character A, essentially A, then 1000001 is sent to the computer. That means, keyboard sends the character code 1000001. So, this some of the ASCII character examples are given here, and this is example of digital data. Now, and another example of digital data is data stored in memory, say CD, have two discrete values which can be represented at 0 and 1. For example, inside the computer, the information that is stored in the form of zeros and ones. Inside the digital computer, it is essentially digital domain. There does not exist anything other than zeros and ones. So, whenever some information is stored in the memory or hard disk or CD, it is stored in the form of zeros and 1, and it is stored in that way. Now, comes the question of signal. So far, we have discussed about data and explained what is data. We have seen that whenever data has to be sent over some communication medium, it has to be converted into signal. Data cannot be sent as it is through the transmission media. We have to transform it into signal before sending over the communication media. So, what is signal? A signal is nothing but it is electric, electronic or optical representation of data which can be sent over a communication medium. That means, we are converting into some form which can be either electric, electronic or optical. It depends on through which medium we are trying to send. That means, when we are trying to send through a pair of wire, it has to be electrical voltage or current. On the other hand, whenever we are trying to send through a optical fiber cable, it has to be converted into optical signal or light. Then that light can be communicated through the optical fiber medium, or it can be sometimes we send some in the magnetic field, in the form of magnetic field. So, we can say it has to be some form which can be electric, electronic, optical, some electromagnetic signal. Again, as we shall see, signals can be of two different types, analog and digital. It can be either analog or it can be digital. And analog signal has continuous values over a period of time, or you can say the infinite number of values over a period of time. For example, here this is an example of an analog signal. As you can see, a microphone converts voice data into voice signal. As you have seen, whenever somebody is speaking or singing, he makes some vibration in the ear. So, that audio data can be converted into audio signal or electrical energy with the help of microphone. That microphone is essentially a transducer which converts from that vibration or pressure on the microphone into electrical signal, generating voice signal, and which can be sent over a pair of wire. Here is an example, say T, and as you can see here you have got that electrical signal with different amplitude values. On this side it is shown. So, this has got infinite number of values. So, it is analog in nature. Similarly, digital signal can have only limited number of defined values, usually two values, zeros and 1. For example, this for example, say this is say 0 volt, say 0 volt, and here it is say plus 5 volt. 0 volt can be considered as 0 logic level and plus 5 volt can be considered as 1 logic level. So, here as you can see that the signal has got two distinct values, either 1. So, here it is say let it be 1 1 0 1 1 1 and 1. So, in terms of ones and zeros, the digital data is converted. So, digital data we are having only two different values. Now, we can focus more on the analog signal. Analog signal can be classified into two types. First one is simple, second one is composite. Example of a simple analog signal is sine wave. Sine wave can be considered as a simple analog signal, and as we shall see, a composite analog signal is essentially a mixture of multiple simple signals, as we shall see very soon. Again, the simple analog signals usually are periodic in nature. For example, a sine wave. Let me draw a sine wave. For example, say so, this is a sine wave I have drawn. Now, this sine wave is repeating, as you can see, after this time. This time t is known as the time period. T is equal to time period. That means, after time t, the signal will be same as the previous portion. The same thing, this part will be repeated here. So, this is another t. So, mathematically, as you can see, when S t plus t is equal to S t for the range minus infinity to plus infinity of time, that means it is starting from any time, it has started long back and it is continuing continuously, it is generated continuously. Then we call it, it is a periodic signal and it has a time period t. This t, capital T, is the time period. Now, a periodic signal can be fully characterized by three parameters. What are the three parameters? The three parameters are amplitude, frequency and phase. What is amplitude? As you can see on this side we have plotted time, and this side we plot amplitude. and this one is known as the peak amplitude. Peak amplitude A, and this what is frequency? So, you have seen peak amplitude A, and that frequency f is represented by 1 by t. That means, if t is the time period, then frequency is essentially is 1 by t. F is equal to 1 by t, that is your frequency. This is actually the frequency. Now, there is another parameter phase, that is for with phase is actually expressed between two different signals, relative appearance of a signal with respect to another signal. For example, this is let us assume this is time t is equal to 0. Here the signal value is 0. So, we can say phase is 0. Later on we shall discuss in more detail about this amplitude, frequency and phase. Now, let us discuss in more detail about amplitude, frequency and phase. Amplitude is the value of the signal at different instants of time measured in volts. And for example, let me represent a sine wave. Amplitude, frequency and phase. Amplitude is the value of the signal at different instants of time. So, if we consider a sine wave, say let me represent the signal st is equal to a sine 2 pi f t plus phi. This is the representation of a sine wave, and this the way as you can see here, A is the peak amplitude, and obviously with time this amplitude varies. For example, as you have seen earlier, it varies like this. Although this is the peak amplitude, that means with time it is varying because of this factor multiplied with it. So, this is known that the amplitude varying with time. And frequency, it is the inverse of the time period, and it is a measure of usually it is measured in hertz. This amplitude is measured in volts, as you can see here. Of course, as we shall see, there are other units that also you use. Frequency, for example, it is inverse of the time period that we have seen, f is equal to 1 by t, and it is measured in hertz. On the other hand, phase, as I told, it gives a measure of the relative position of two signals in time expressed in degrees or radian. Let us see examples of signals with different amplitudes, frequency and phases. For example, this signal this particular signal as you can see has got amplitude 1 volt, peak amplitude 1 volt. So, A is equal to 1 volt, and peak amplitude 1 volt, as you can see here, this part is 1 volt, this is 1 volt, within 1 second, you can see in 1 second one complete cycle is completed. So, it has got frequency f is equal to 1, and as I told, in time 0 the phase is 0. So, phi is equal to 0. Now, here is another signal. Here amplitude, as you can see, this is 0.5, the peak value is 0.5 with respect to this we can compare. So, this is 0.5. So, A is equal to 0.5, frequency is same, it is repeated after 1 second, and here also phase is 0. Here on the other hand, the signal as you can see, within 1 second there are 2 complete cycles. So, it has frequency here frequency f is equal to 2, although amplitude A is equal to 1 and phase phi, in this case it is 0. So, it has here we have got amplitude is equal to 1, frequency is equal to 2 and phase is equal to 0. Now, in this diagram we have got phase, as you can see, with respect to this, everything is same with respect to this except phase. So, it is not starting with 0, that means 0 volt is not at 0 point, and there is a phase shift of about 45 degree, and phase is expressed in terms of degree or radian, as we shall see. So, in this particular case, A is equal to 1 volt, f is equal to 1 hertz, 1 means 1 hertz, because in 1 second again one cycle is completed, and phase is equal to 45 volt. So, here we see we have varied, we have taken example with different amplitude, frequency and phases. Now, let us take consider the for different parameters that we have discussed, amplitude, frequency and phase, let us consider their other units that is commonly used. For example, say let us consider first for amplitude, say amplitude. So, it is in volts, but sometimes the voltage can be of very small. So, in such case we can call it millivolt, then we write MV, millivolt, that means which is equal to 10 to the power minus 3 volt. Or sometimes we have to represent high voltage, then we can say that it is kilovolt, that means it is 10 to the power 3 volt. Similarly, for frequency, as we know, the normal the way we call it, it is hertz, but sometimes the values can be very large. So, we call it, say sometimes the frequency can be very high, then we say kilohertz, that means 10 to the power 3 hertz, or it can be megahertz, that means 10 to the power 6 hertz. This is your 10 to the power 6 hertz, or it can be gigahertz, that means 10 to the power 9 hertz, or it can be terahertz. That means, you see, we are dealing with very large frequencies nowadays, 10 to the power 12 hertz. Similarly, for time period, or sometimes we call it period, the unit, basic unit is second, S. which we represent by s. But sometimes we have to deal with very small time or very long time. Say we have to write say millisecond, that is equal to 10 to the power minus 3 second, or microsecond, that is equal to 10 to the power minus 6 second, millisecond, microsecond, or nanosecond, 10 to the power minus 9 second, or it can be picosecond. Sometimes we have to say write very small time, picosecond, 10 to the power minus 12 second. So, these are the various units for amplitude, frequency and phase. Similarly, we can have units for say phase. Phase we have seen within one that within one cycle, say in this range, the phase can vary 360 degree. So, in the from here to here, that means this is 90 degree, this is 180 degree, this is 270, this is 360, or we can express it in radian. In that case it is 2 pi. Suppose the phase has been shifted by this, the another signal is like this, that means it is here the phase is about 45 degree. So, in that case it is 45 degree, and which can be written as 2 pi by 360 into 45 in radian. So, we have seen the various units used to represent the important parameters, amplitude, frequency and phase for a signal, and we later on we shall see these are the parameters that we shall vary for the purpose of communication through medium. Later on we shall discuss about that. Now, we have discussed about the time domain representation of the signal. On the x axis we have plotted time, and the amplitude variation with time we have shown, and this can be visualized with the help of a oscilloscope. Oscilloscope is the equipment that is normally used to have visualization of the time domain representation of the signal, and we are very familiar with that. However, whenever you vary the amplitude, phase or frequency, it becomes a composite signal, and that composite signal, whenever it is shown on the oscilloscope, does not convey much meaning to us. In such a situation, it is better to have frequency domain representation of the signal. And whenever a signal is complex, by virtue of the variation of parameters like amplitude, phase and frequency with time, then it becomes a composite signal, and that composite signal, according to Fourier analysis, any composite signal can be expressed as a combination of simple sine waves with different amplitudes, frequencies and phases. That means, we can express any signal, composite signal, in terms of sine waves having frequency f1, having frequency having frequency f2, having frequency f3. So, it is an infinite series, many frequencies. Now, here is an example. So, here we see this is a sine wave, sine 2 pi f1 t having frequency f1. This has got frequency f1. Here is another signal as you can see, within this you have got we have got 3 cycles. So, it has got frequency 3 f1. So, this frequency is 3 times of that. Now, if these two are combined, these two are added, that means say sine, say if we have suppose we have sine twice pi f1 t plus 1 by 3, that means amplitude is 1/3 sine twice pi 3 f1 t, assuming that phase is same for both, phase is 0, then if we combine these two we get a signal like this here as it is shown. That means, here as you can see we have got combination of these two sine 2 pi f1 t plus 1/3 sine 2 pi 3 f1 t. So, if we combine this and if we see it on the oscilloscope in the time domain, we shall get this kind of diagram. This is the diagram we shall get in the time domain. However, if we analyze it with Fourier series, then we know that it has got two frequency components, one of f1 and another of 3 f1. So, here you see this is the frequency domain representation. On this side you have got f, and this amplitude corresponds to the amplitude of this frequency, and here 2 and 3. So, here it is 2, here it is 1 and here it is 3. So, you see 3, that waveform with 3 amplitude has got frequency 3 f1. How we can see this? This can be visualized with the help of a special equipment known as spectrum analyzer. So, spectrum analyzer is an equipment which can give us frequency domain representation of the same signal. Now, this frequency domain representation, as you can see, gives us the information about the different frequency components the signal has got, and which is sometimes very useful to us. So, now let us consider several examples of time domain and frequency domain representations. So, here we see this diagram A gives you the a signal having this is the 1 second, and within 1 second how many pulses are there? 1, 2, 3, 4, 5, 6, 7, 8. So, it has got frequency f and time period is equal to 1 by 8 second, and so we get, and this corresponds to 5 volt, 5 units, maybe 5 volt. So, you see if we have a look at the frequency domain representation, we get a line here at frequency f is equal to 8. On the other hand, here is another signal which has frequency 16. If you count, you will get 16 full periods within 1 second. This is 1 second. So, it has got time period 1 by 16 second, and frequency domain representation is given here. We get a line of the same voltage, as you can see here, same voltage and with amplitude 5. Now, whenever we are considering particularly a digital signal or a composite analog signal, as you have seen, it comprises many frequency components, and that is expressed in terms of frequency spectrum. And frequency spectrum of a signal is the range of frequencies a signal contains. For example, here is a square wave, and the square wave has time period t and frequency f. Here say f is equal to 1 by t. Now, this square wave has got, if we represent in terms of I mean expand it with the help of Fourier series, it will have the representation ST is equal to say A is the amplitude, and that means it will have the amplitude A by 2 pi sine twice pi f t plus A by 6 pi 1/3 twice pi 3 f1 twice pi into 3 f t, that means it has got third, the frequency is 3 times, plus A by 10 pi sine twice pi into 5 f into t. So, here sorry, I forgot to write this expression properly. So, here actually it will be A by 6 pi sine 6 pi f t. So, in this way it will have all the frequency components, say frequency component of 3f, 5f, 7f, 9f and so on. However, as you can see here, the amplitude is gradually decreased, A by 6 pi, A by 10 pi, A by 12 pi, like that it will keep on falling. So, but however, it will have a frequency component of infinite frequencies. So, all the frequency components starting from f to infinite components. However, the frequency components of higher frequencies will be lower. So, these are known as harmonics. So, this is the third harmonic, this is the fifth harmonic, it will have seventh harmonic, ninth harmonic and so on. So, increasingly lower amplitude. Now, whenever we are representing a signal, we have seen that the frequency spectrum can be very large. However, most of the frequency components having very small amplitudes are of not much use. That is why there is another parameter known as bandwidth represents the frequencies over which most of the signal energy of a signal is contained, or it is the this bandwidth can be effective bandwidth of the signal. Here the term, that means the range of frequencies over which most of the, look at this term most, that means so here is the information about bandwidth. For example, your you are interested in representing the bandwidth. Suppose this is the frequency domain representation and a signal having and this side essentially signal strength or amplitude. It has got infinite frequencies in this range. Obviously, the frequency of the spectrum of the signal is spreading over from from lowest to highest frequencies. However, for all practical purposes, we can remove this if we remove this portion, similarly from this side, so if we remove this portion of the spectrum, then we can say this is the bandwidth. So, this is the bandwidth of the signal, from this part to this part is the bandwidth of the signal. So, this is where the major part of the frequency components or energy is lying. So, we call it the bandwidth of the signal. Now, in case of digital signal, as we have seen, it can be aperiodic in nature. It may not be periodic in nature like the simple analog signal like sine wave. So, in such a case it can have infinite number of frequencies. Now, in the context of digital signal, there are two parameters known as bit interval and bit rate, which you have to discuss. For example, bit interval, it is the time required to send a single bit. For example, this is a digital signal, say this is 1. So, this is your this is the intervals, say 1 0 and then it can be 1 1, and this interval is essentially the bit interval, say this time t is the bit interval, and bit rate is the, if bit interval is t, then the number of such bits can be sent in 1 second is essentially 1 by t. So, and this is known as the bit rate, the number of such symbols that can be sent in 1 second, and it has the expression bits per second. Obviously, it can be extended to kilobits per second whenever you are sending 10 to the power 3 bits per second, or it can be megabits per second when you are sending 10 to the power 6 bits per second, or gigabits per second, 10 to the power 9 bits per second. So, these are the rates, bit rates that are commonly used. Now, whenever we are sending analog signal, then the bandwidth is restricted within certain range. On the other hand, whenever we are sending a digital signal, bandwidth is very large. So, this can be represented in two forms. So, for example, a digital signal can have spectrum like this. That means, this is the bandwidth. This is for digital, 0 to very large frequency. On the other hand, for analog signal, we may restrict it within certain range, So, bandwidth is essentially like a band pass, and here it is like low pass, as you can see, from 0 to certain high frequency. And because of these characteristics, through one medium we can send only one digital signal. On the other hand, we can send several analog signal, like say another analog signal, another analog signal. In this way we can say in a frequency division multiplexed manner. So, this is the frequency, and several such signals can be sent through the medium. On the other hand, digital signal cannot be sent this way. Now, there is another important parameter, that is propagation time. It is the time required for the signal to travel from one point of transmission medium to the another, and it is essentially the distance by the propagation speed. And there is a related parameter, wavelength. It is the distance occupied in space by a single period. Obviously, there is relationship between the two. Wavelength is equal to propagation speed into period, or propagation time into frequency. Let me explain with the help of some example about the speed and frequency. For example, speed of electromagnetic signal in free space is 3 into 10 to the power 8 meter per second. Now, that lambda, that means this is equal to the speed of light. Lambda is equal to c by frequency, the speed of light by frequency. For example, the wavelength of red light is equal to 4 into 10 to the power 14 hertz. What is the wavelength of this? This is the frequency. What is the wavelength of red light? Lambda is equal to 3 into 10 to the power 8 by 4 into 10 to the power 14 meter. That is equal to 750 nanometer. So, you see the frequency is very high, but wavelength is small for the red light. So, this is how the speed and propagation time can be correlated, and this is the speed in free space. Obviously, whenever it is sent through some guided media, as we shall see, then the speed will be smaller, will be equal to say 2 into 10 to the power 8 meter per second. So, we have covered different topics related to data and signal. Here are the review questions on this particular lecture. The questions are: distinguish between data and signal. What are the three parameters that characterize a periodic signal? Distinguish between time domain and frequency domain representation of a signal. What equipments are used to visualize electronic signals in time domain and frequency domain? Distinguish between spectrum and bandwidth of a signal. So, these questions will be answered in the next lecture, and we end this lecture with the answers to the question of lecture 2. First question was: why is it necessary to have layering in a network? The answer is, as we know, a computer network is a very complex system. It becomes very difficult to implement as a single entity. The layered approach divides a very complex task into small pieces, each of which is independent of others, and it allows a structured approach in implementing a network. Second, this is the answer to questions of lecture number 2, and this is the answer to question number 3 of lecture 2. Thank you.